You know, in machine learning, we're always walking this tightrope between making a model too simple and making it way too complex. If you go too far in either direction, your model is basically useless. Today, we're going to break down this fundamental balancing act, the bias-variance trade-off. So let me paint you a picture, and I bet you've been here before. You build a model, you train it, and boom, 99% accuracy on your training data. You're thinking, I nailed it. But then you deploy it, and it just completely fails in the real world. So what happened? This isn't some weird bug. It's a core concept that, once you get it, changes how you build models forever. And that brings us right into Act 1, the problem. I like to call this the training data trap. It is so tempting to just obsess over how well your model performs on the data you have, but trust me, that is a huge mistake. See, the real goal here isn't to build a model that's just a great history student, one that can perfectly memorize every single fact you show it. No, we need a model that's more like a prophet, one that can generalize from what it's seen to accurately predict the future on data it has never encountered before. A model that only memorizes is, for all intents and purposes, completely useless. Okay, let's think about it this way, with a super simple analogy. Trying on a t-shirt. An underfit model? That's like a shirt that's way too big and baggy. It completely misses your actual shape. An overfit model is the opposite. It's like a shirt that's so tight it shows every single contour, but you can't breathe or move. If you gain a pound, it's gonna rip. What we're looking for is that balanced fit, the one that's just right. And that's exactly what we want from our models. All right, so how do we actually diagnose these fitting problems? Well, that's what Act 2 is all about. We're going to introduce the two key terms you absolutely need to know, bias and variance. First up, let's talk about bias. Think of bias as the error you get from a model being too simplistic, too stubborn in its assumptions. Imagine you've got data that clearly follows a curve, but you're trying to model it with a straight line. No matter what you do, that straight line is always going to be wrong. It's systematically missing the point. That error, that stubbornness, that's bias. And then you've got the total opposite, variance. This is the error you get when your model is too flexible, too sensitive. It pays way too much attention to the specific data points you trained it on, including all the random noise. The result, if you were to retrain that same model on a slightly different set of data, you could get a wildly different outcome. That instability, that shakiness, that's high variance. So let's put them side by side to make it super clear. High bias, that's underfitting. Means your model is way too simple. It misses the real pattern, and so it performs poorly, even on the data it was trained on. High variance, that's overfitting, is the opposite problem. The model is so complex that it doesn't just learn the pattern, it learns all the random noise too. So it looks amazing on the training data, but then it fails miserably on new data. And here is an absolutely golden rule to remember, a fantastic little mnemonic. When you're thinking about bias, you're really thinking about your training error. If your training error is high, you've probably got a bias problem. But when you're thinking about variance, you're really thinking about the difference between your training error and your test error. That gap is where variance lives. So what does underfitting look like in practice? Well, it's kind of obvious, actually. The model is just bad everywhere. It's too simple, so it can't capture the underlying trend. This means you get high error on your training set and you get high error on your test set. It's failing across the board. Now, overfitting. This one is sneakier. This is the model that looks like a total genius on your training data. The training error is incredibly low because it has essentially memorized every single data point, noise and all. But the second you show it some new, unseen data from your test set, it completely falls apart. That huge gap, low training error but high test error, is the giant red flag for overfitting. And this right here, this is the heart of the problem. You can't just get rid of one of these errors without affecting the other. As you try to decrease bias, you almost always increase variance, and vice versa. This is the classic bias-variance trade-off, and our entire job is to find that perfect balance, that sweet spot. Okay, think about it like this. As we start making our model more and more complex, maybe we add more features or more layers to a neural network, it gets better and better at fitting the training data. It's more flexible, so it can capture those tricky patterns. In other words, its bias goes down. But, and this is the crucial but, as you keep making it even more complex, it eventually starts to go too far. It becomes so flexible that it doesn't just learn the pattern, it starts memorizing the random noise. It becomes hypersensitive to the training set. And what does that mean? Its variance starts to go up. And that gives us the whole picture, this famous U-shaped curve. Your total error on new data is a mix of bias and variance. At first, as your model gets more complex, total error drops because you're slashing that bias. But you'll hit a point of diminishing returns, where the rocketing variance starts to hurt you more than the decreasing bias helps you. The best model, the sweet spot, is right there at the bottom of that U, where we found the perfect balance. Okay, theory is great, but how do we actually fix this stuff? How do we find that sweet spot in the real world? That brings us to Act 3, the solution. This is your practical toolkit. This table right here, this is your cheat sheet, your diagnostic guide. You just look at your training error and your validation error. Are they both high? Bam, you're underfitting. Is your training error low but your validation error is high? That's the classic sign of overfitting. And if they're both nice and low, congratulations, you've probably found a good fit. So what if your diagnosis is overfitting, high variance? The game plan is to rein that model in, to simplify it. You can use something called regularization, which basically penalizes the model for being too complex. Another great fix is to just get more data. It's way harder for a model to memorize noise when there's a ton of data. Or you can manually reduce the model's complexity yourself, maybe by using fewer features or layers. And if you're underfitting, well, you do the exact opposite. Your model is too simple, so you got to give it more power. You can try a more complex model type altogether, engineer some new, more useful features for it to learn from, or if you're using regularization, you can dial it back to give the model more freedom. Whew. Okay, we have covered a ton of ground, so let's boil it all down to the final takeaway, the stuff you absolutely need to remember. All right, here's your 1-minute summary. If you remember nothing else, remember this. Underfitting means your model is too simple. That's high bias. Overfitting means your model is too complex. That's high variance. Our goal is always generalization, not memorization. And the key, the absolute key to finding that sweet spot is to watch your validation error like a hawk. That, not your training error, is your true north. Okay, I'm going to leave you with a little challenge, a pop quiz, if you will. Let's say your model hits 95% accuracy on the training set, but only 70% on the validation set. What's the problem here? Overfitting or underfitting? And what's the very first thing you try to do to fix it? If you can answer that, you're well on your way to mastering one of the most important concepts in all of machine learning.